Okay, good afternoon, everyone. So sorry for the delay. We actually on a 45-minute delay in this lecture. Anyway, there are some background things are going on, so we cannot avoid everything. So let us start this story of course again. And there is a 12th grade, 2022, and we are having the session 105. Okay, so in this lecture, we are supposed to talk about the type of fluids. We actually talked about the type of fluids kind of in the second class. That is, we are having different fluids, their properties. So let us go back to that and let us understand more in the deeper sense that how this different types of fluids like you can see the categorization like something liquid, something gas, something maybe plasma. But that is kind of physical difference. You can say based on the density, based on some other physical properties, and also we divide the fluids in terms of the dilatation. So based on that, we have Newtonian fluid, non-Newtonian fluid, plastic fluids. So let us also we can relate the Newtonian fluids as kind of ideal fluids and non-Newtonian that is having some dilatation that is more or less real fluids that what we see everywhere around unless we have some specific condition for that particular fluid. So what we have drawn last thing that stress versus strain. So this is strain and what we can draw for the ideal fluids. This is the relation between stress and strain. So that would be linear. And for ideal, it has to be the 45 degree. So we know the stress. So tau. Del y. So if this is proper, so that might be 1. So we can just relate. This is strain basically, and this is stress. This is strain. So if this is possible, that means the stress and strain are equal. That is u equal to 1. So that is very much kind of explaining this, the 45-degree line. So because of strain remains same, whatever the increase in 1, so that will depict this 45-degree line. But more you go towards the real fluids, that won't be following this. This is basically the ideal one. So this is the Newtonian equation. So whatever following this properly, that is called the Newtonian fluid. But non-Newtonian fluid, that generally does not follow this. So it may be plastic. So if there's a heavy strain, that can change after some time. So that is more or less plastic. And also we have more dilatant fluid, non-Newtonian. That will be like this. So this one basically having pure plastic fluid, that maybe it will start the dilatation, the strain will be visible even not for the zero. So for very little amount of external forces, there will no change. Okay. So that basically uh, very much of ideal plastic fluid. So that is basically after some stress, that basically removes the internal resistors, and then it starts to change. So that is kind of ideal plastic fluid. So these are the basically different types of fluid that we generally think of, because we are very much worried about its behavior under stress, yeah, under external forces. So basically, when you flow a liquid, or you transfer the liquid, or you try to transfer the forces from one point to another, that is most of the hydraulic system what we generally use in mechanical engineering, in automotive engineering, or even in the petroleum and other sectors. So transferring the load and the behavior of the fluid under this load, that will be very much important for us to understand. So that's why the categorization of the fluids are more generically important into this, is a dilatant or not, is a Newtonian, ideal or the real. So these will be more important than what we categorize as the liquid, gas, and plasma. We'll talk about this definitely in detail, maybe some other classes, because plasma is not considered as either the this either liquid or gases. It has a high amount of charged particles. So what happens in the outer atmosphere and also in the core of the Earth, that is we have in the plasma, that is between the gas and liquid. So the behavior of plasma definitely is different. But whenever we talk about the industrial arena or the academic, without going to very specific research, these classification or the types may not be that important for most of us, but definitely these are also having very intricate details, and also the chemical and physical property differences, and how we design that, how we deal with this. Nowadays, people are talking about the fusion and all, fusion energy. We are looking into the more in the renewables, more in the uh, non-conventional energy. So the fusion reaction and all, we are dealing with the plasma and how we keep that, how we uh, kind of contain the energy. So all these are coming up, but we are not exactly covering it today. So that will be there in the deeper sense. So basically, what the class we have is more or less overview, and what people, most of the people will basically get interested in. So that's why we are talking more about this dilatation. So as we just mentioning in some previous classes that dilatation is nothing but the movement of the particles. So that has been some internal bonding. Maybe you can think about some petroleum, nitrogen, and carbon and hydrogen are binded together. So in this kind of structure, there may be this is a more or less very generic structure, and you know the carbon structure is hexagonal and sometimes a deca. So that will come later. And just to understand the dilatation and its effect on the type of fluids and how we basically kind of do the force transfer to the liquid or the fluid. So that is important for most of us when we talk about the industrial application or not. So if we put some forces or maybe the stress over an area, that is pressure. So some part of the liquid body that will encounter the external forces. Like if you have a piston, you have liquid, and this piston and some external load or forces. Sometimes we use load or force F. So this, when you put this on this very particular liquid, what will happen? Like let me just try to resemble the same thing here. So vertical downward forces. Definitely G is always working. Now extra load is here. Nothing is submerged, so we can forget about the buoyancy and all. So if the external force is working on this, so how much load will be transferred to this layer, layer to layer? That will depend on the physical characteristics that we generally talked about, the viscosity, or viscosity is what? This is the relation between the stress and strain. So how the fluid will act based on strain and kind of reveal the strains under the stress, that is basically depending on the structure. So structure and the structural strength of it. So if the molecules, what the bonding it's here, so that is basically very kind of loose bonding, so easily they can tumble. What will happen if the bondings are too weak? So this molecule will be squeezed, right? So that is basically happens when you have gases or very low viscous, low density liquid. So this is bound to squeeze. So this, like any gas, you can put process, but definitely there will be a minimum energy that is still there that will kind of react to the external force. So this reaction, this is F, sorry, this sign has to change. So action and reaction, they can balance, and then only this movement of this piston has to stop. None of this. So this will happen only when the what are the minimum warning we have that starts to resist. And when the resistance balance the external force, they will be in a equilibrium phase. So that's what happens within these structures, and these structures are very important. We are nowadays we are developing graphenes and other special materials, some liquid also, the superconductor liquid we are trying to develop so that we can transfer the different energy like solar energy and also geothermal energy. So nowadays we are trying to use different kinds of special fluids. So any kind of special fluids, we have to go into the deeper sense of the particle properties or the molecular properties, as well as its overall properties, the bulk properties. So property-wise, that also quite different when you talked about different scales that we already discussed. So it's basically that how we deal with those fluids. So maybe a liquid having the difference in the density and viscosity, that is sometimes irrelevant when you talk about is mass transfer. So when you are just transferring the mass from one place to another, so only the wall friction that will be much more relevant than the internal frictions if it is not that much viscous fluid. So it depends on what type of work you do and what type of action you have on the fluids. Like if you are just doing an experiment, the Bernoulli's equation, or maybe the energy balance or the momentum balance. Bernoulli's equation basically gives you the energy balance, or you do the momentum balance, that is just using the impact of a jet on the plate that is having some moment get transferred, and that is because of the lever system, we are getting different kind of load transfer, and that load and the momentum change that we can relate with. But in case of that experiment, if you think of using different fluids, that won't change the scenario. That won't change your target in that drastic fashion. But when you are kind of doing an experiment on buoyancy or kind of the frictional flow, the frictional resistance, maybe the Dusty wave drag function or the factor that we are trying to calculate. So their viscosity or the density have a major role to play with, and that definitely kind of give you more insight into the properties of the fluid uh, rather than just overall the bulk kind of characteristics. So depending on that, we have to choose different types of fluids. And when you talk about gases, uh, we transport gas mostly in kind of liquid form, because transferring the gas in the gaseous form, that takes much more space than the liquid. So transferring volume or canister volume or maybe the pipe diameter that we require, that is basically much more larger and sometimes uneconomic for that kind of transport. So that's why people are using the hydraulic systems or just the universal gas equation, that is equal to nRT. And if we keep the temperature very low and also high pressure, we can reduce its volume. We can transfer or force the phase change. Definitely, there will be much more energy is required when you talked about the phase change, because what are the specific heat that has to be extracted out. So that is basically the uh, thermal change that you are looking at. So that definitely needs more energy. So when you have that kind of option to use a higher energy versus that the lower volume we can get, definitely we can go for that. But other than that, we have to just use some kind of transfer mechanism in the pipe and enclose things because of the gas thing. Now things got changed when you talk about the gases in the atmosphere. So atmospheric conditions, that is more or less Lagrangian condition when we are thinking about a particle, maybe that is a rocket or maybe a boat rocket in the air moving up to the atmosphere, or maybe we can think of the boat is moving over the surface of water, or maybe a submarine moving inside the water. So in that case, the fluid behavior around that kind of object is much more important, because we don't have the conduit here is all open, and that is under gravity. So that is a different kind of game, but all the properties, what we viscosity, density, kind of specific density, the specific heat, all things will be remaining same. But the flow pattern, but how the fluid flows through, that will definitely change. So that flow pattern, the movement, or kind of diversion from its original path, that also will be depend on not only the shape of the object but also the uh, characteristics of the or the properties of the fluid. So diversion is a different thing. So we can have kind of drag forces that will be acting upon that particular object, and some frictional drag that will develop whenever it is moving over that particular surface, and that actually creates some force that will kind of push that particular object through that medium or the fluid. It can be air or it can be water, anything. So in that case, definitely, as I told, not only the geometry or the shape of that object, but also sorry, also the properties of the fluid that will very much kind of predominant or kind of important for us to kind of study. So that is very important, and that's how we'll be looking into some kind of flow patterns. You may heard of the string lines, strict lines, path lines. So this is basically the fluid dynamics. And after we finish fluid statics part, the some numerical problems we do on this part. So fluid statics, basically the when fluid is a static part, like without any movement, without any velocity. So what are the different properties it can generate? And that will definitely help us to understand the behavior of fluid. You can utilize the fluid properties like the force transfer, the pistons, or the lifting things. So also we can use the fluid for transferring the energy from one point to another. That is sometimes required. Mostly we use a more conductive fluid, not the water. Water is very high uh, or very low conductivity, very high resistance to the thermal change. So definitely highly conductive gases or liquid we should use. So in that case, that we generally utilize in fluid of the fluids. So we also have kind of different kind of framework, I should say, to understand the behavior. So we will try to understand the behavior, the fluid patterns, and that you may just remember in the first or second class we have discussed the fluid patterns in the turbulence that drawn by the Leonardo da Vinci, and they he used basically the hair, the kind of very smooth movement of the fluids. So that is very much a characteristic of the fluids. It try to move all along its path. So whenever it takes a bend, it try to follow the original path as far as possible. So that is because it can dilate. Most of the real fluids that we discuss here, that can dilate itself. So that can deform itself. So this deformation, sometimes it can dilatation. If you have the horizontal forces here, and this is fixed, so it will move further in the direction of the force, and this will be static. So these dilatations are very much possible, and that's why this movement of the fluids are more smooth than the movement of the solids. So we'll talk about that, and we'll do some kind of very interesting numerical problems on the fluid statics. So that will be covered in the next class. So because of the network problems and my health, let us just conclude it today here for half an hour. And next week we'll meet again and we'll start working on some numerical problems. So whatever the theory that we are discussing here, that will be more kind of clear to you, and that will help you to understand in more detail. So there we will definitely look more into the more the equations and the more notations, because whenever you solve a problem, you should know the equations properly. So without equations, just putting the values is not that uh, valid. So unless you know the background science, you cannot apply that. So that will be there in the next class. So just excuse me and let us conclude here. So this video will be available in my YouTube channel, and you can look at it anytime. But I'm telling you, literally, these are kind of very overview kind of classes. So detailed class will definitely start in June with maybe more faculties with me for different subjects, and that will try to engage with a professional platform. So that will help us to go bigger and to bring you more insight into the subject. So till then, bye bye. We'll see you in the next class.